Hello everyone, my name is Jinyu. I received my PhD degree last year, and now I am a young faculty in Shanghai Jiao Tong University. I'm glad to introduce our work to you. This work is entitled EPK, Scalable and Efficient Memory Protection Keys. Inter-memory protection key, known as InterMPK and InterPKU, it is a hardware feature for intra-process memory isolation, which has been introduced into Intel CPUs since 2019. Both the desktop and server CPUs are shipped with this feature. It offers highly efficient intra-process memory isolation by supporting memory domains inside one application. Specifically, InterMPK can divide the virtual memory space of one process into 16 memory domains. By leveraging previously unused 4 bits in the page table entry, each memory page is tagged with a 4-bit protection key as a domain ID, and exclusively belongs to one of the 16 domains. A new 32-bit register PKRU is introduced to specify the access permissions, including read-only, read-write, and none on the 16 domains, 2 bits for one domain. Because the register is per core, concurrent threads in the same process can have different access permissions on different domains. A non-privileged instruction called WRPKRU can update this register to change the access permissions. Notably, this new instruction not only can execute in the user mode directly, but also takes only about 28 cycles. According to prior studies on MPK-based intra-process isolation, the common usage model of MPK is as follows. An application process creates memory domains by binding different protection keys to them as the domain IDs and separates the memory data into different domains. An application thread acquires or releases the access permission of one specific domain before or after accessing the data in it, which reduces the chances of isolated memory being affected by vulnerabilities or faults. Acquiring or releasing the domain access permission is efficiently achieved by executing WRPKRU instruction, which is referred as domain switching. However, the small number of isolated memory domains supported by MPK undermines its usability. Here are some potential scenarios that desire lightweight isolation while MPK fails to fit due to the problem of non-scalable domain number. First, a typical server application usually serves for more than 16 clients concurrently, and it is preferable to store clients' private data in isolated domains to prevent sensitive data leakage. Second, there is a growing interest in protecting persistent memory data from accidental or malicious accesses. Isolating the data in more domains can reduce the data exposure time and benefit strict access protection. Third, both applications and system software may contain more than 16 components that need to be isolated. For example, popular applications use scores of third-party libraries. The root cause of why MPK can only support 16 memory domains is that each domain needs to exclusively take one PK, while the hardware only supports 16 PKs in all. One candidate design choice is resource time division multiplexing, which means letting different domains use the same PK at different times by evicting the PK from one domain and assigning it to another domain. However, such a solution may lead to a non-negligible performance overhead. For example, if we want to reuse PK1 for another domain, name domain 17, we need to first clear all existing PTEs tagged with PK1. This procedure can be costly, especially when the domain memory size is large, because we need to modify many PTEs. Besides the overhead of page table modification, we also need to flush TLBs, which will further introduce more overhead. Another very intuitive solution is using more bits in the page table entry as the domain ID. For example, if 10 bits instead of 4 bits are used, it can offer 1024 memory domains. However, this is infeasible on commodity machines and may be incompatible with the upcoming 5-level page table because of using too many PTE bits. Moreover, how to represent the domain permission efficiently is also a problem, since it cannot simply use one PKIO register with more than 2,000 bits. So, our work has 3 major design goals. First is to support a scalable number of memory domains. Second is no hardware modifications is required. Third, low performance overhead, especially it needs to support a scalable memory domain size. MPK's performance advantage stems from the decoupling of domain configuration in the privileged mode and domain switching in the non-privileged mode. Our observation is that another hardware feature, VMFUNC, for fast EPT switching has a similar pattern, which decouples EPT configuration in the host mode from EPT switching in the guest mode. Thus, we propose extended protection keys by combining MPK with fast EPT switching, which means reusing the same MPK protection keys in different extended page tables. Different from time division multiplexing, one PK can be simultaneously used for different memory domains in different EPTs. EPK is short for Extended Protection Keys. Here is a quick introduction on VMFUNC. As we know, Intel hardware virtualization employs EPT for memory virtualization. For a virtual machine, the page tables inside the VM map guest virtual addresses to guest physical addresses, while the EPT maps GPAs to host physical addresses. The hypervisor manages the VM's EPT. VMFUNC is a hardware instruction allowing the guest VM to directly load a new EPT. The loadable EPT can only be chosen from a list of EPTs up to 512 configured by the hypervisor. The hardware feature of MPK is also usable in a VM, thus EPK combines MPK and VMFUNC. It requires an application to run within a VM and multiple EPTs need to be created for the VM. EPK allows an application to partition its virtual address space into different memory domains, with each domain containing discrete memory pages. A domain exclusively takes one extended protection key as its domain ID, which is composed of a P key and an EPT index. Each EPT can hold 15 domains for an application, and the 15 domain IDs have the same EPT index but different P keys. For example, domain 1 and domain 2 are both in EPT 0, but use P key 1 and P key 2 respectively. The same P key can be shared by domains in different EPTs concurrently. For example, domain 1, domain 16, and domain 31 can all use PK1 because they will be mapped in EPT0, EPT1, and EPT2 separately. Memory isolation between domains within the same EPT is achieved through the use of distinct PKs. To achieve memory isolation between domains in different EPTs, EPK ensures that each domain's mappings only exist in one EPT. Other memory pages, like the global code and the data, are tagged with PK0 and mapped in all the EPTs. EPK calls this special domain as domain 0. This is also why each EPT can only offer 15 domains instead of 16. EPK preserves the usage model of the original MPK. It includes a user library to provide interfaces for applications. An application can invoke alloc domains to get multiple domain IDs, considering that some domains are likely to traverse together. The interface will try to return the domains that are located in the same EPT because domain switching within the same EPT is faster. Domain map is used to allocate virtual memory pages within one memory domain. Domain begin and domain end are responsible for switching memory domains. Switching between domains within the same EPT can finish by executing WR-PKIU instruction for setting the PKIU value. Switching between domains in different EPTs involve one additional VMFUNC instruction. While the idea is simple, there are two implementation challenges for combining MPK and VMFUNC. First, how to make a VM seamlessly run with different EPTs, and the hypervisor does not have domain mapping information. How can it tell a legal EPT violation caused by on-demand paging with an illegal one due to a wrong access? Second, given that MPK allows one thread to access multiple domains simultaneously, how to support such a flexible feature when multiple EPTs are in use? Due to the time limitation, please refer to our paper for detailed designs if interested. We conduct the experiments on a Dell PowerEdge server. Besides the vanilla process, we compare the performance of EPK with a VMFUNC solution and libmpk. The VMFUNC solution provides one memory domain in one EPT and leverages VMFUNC for domain switches. libmpk is a pioneer study that extended MPK memory domains. It uses the technique of time division PK multiplexing. Since it does not need virtualization, we run it in the host OS for fairness. We first apply different intra-process isolation mechanisms to a widely used web server, Nginx. To evaluate the performance overhead, we isolate SSL session keys of different clients in different memory domains. We leverage AB to generate the workload. 300 clients keep sending file requests one by one, thus the total domain number is 300. EPK imposes about 5% overhead compared with native and outperforms the other solutions. The overhead of the VMFUNC solution is about 12%. We make the server thread handle client requests in order, thus most domain switches in EPK need no EPT changing, making EPK outperform the VMFUNC solution. libmpk incurs about 18 performance overhead due to the involvement of page table modifying and TLB flushing. Bringing intra-process memory isolation to protect NVM data has also been investigated by recent work. In this case, we create multiple memory domains with different mechanisms, and each domain contains one hash table. In this test, we fix the domain number to 32, while increase the domain size by adding more buckets and key value pairs in each hash table. The overhead of libmpk increases as the domain size grows. because it needs to update more page table entries during domain switch. In contrast, the overhead of EPK and VMFUNC solution is immune to the domain size. The overhead decreases because the vanilla performance decreases when more memory involves. Here is a last case study. Microkernels leave minimum functionalities in the kernel while running system servers, such as file systems and device drivers in the user processes. The interactions between two servers or between an application and a server require InterProcess Communication, which is not cheap. A most recent IPC design called On-the-Bridge retrofits Intel MPK to optimize IPC. It pulls system servers from user-level processes into the kernel address space. Meanwhile, it leverages Intel MPK to ensure the isolation between system servers. The IPCs between the servers are based on WRPKRU instructions and thus greatly optimized. However, due to the MPK domain number limitation, it can only accelerate IPCs for limited system servers. Since EPK can construct many more isolated memory domains efficiently and enable fast domain switch at user level, we propose EPK-based hybrid for boosting IPCs for microkernels. System servers run at user level, and each one exclusively take one private memory domain for holding its own memory, such as code, data, and stack. The system servers cannot access each other's private memory, just like when they are isolated in different processes, while IPCs are based on the efficient domain switches. The microkernel can run the related system servers in the same EPT. Then most cross-server IPCs only need to execute WRPKRU instruction for switching memory access permission. The application to server IPC needs to execute VMFUNC to change the EPT, which is also far more lightweight than the original microkernel IPC. On our research microkernel Zhicao, hybrid shows better performance than the two recent IPC designs, On-the-Bridge and Skybridge, which use MPK and VMFUNC to accelerate IPCs respectively. In the case of running SQLite on Zircon, which is a microkernel from Google, hybrid can outperform the native performance by up to 9 times and outperform Skybridge by about 66%. To conclude, EPK is a first trial to combine the usage of MPK and hardware virtualization features to achieve scalable and efficient intra-process memory isolation. The 3 case studies demonstrate various potential usage of EPK. Thank you very much.